Okay, let's look at properties of logarithm functions. And consistent with your experience in the real setting, the properties or identities involving logarithms are going to be based largely on properties of exponential functions, which we established a few sections back. First, lemma 3.32.8. For the multiple valued function, you know how I feel about that. Log z, defined a few sections back, we have for all z1 and z2, non-zero, complex numbers, that the log of z1, z2 equals the log of z1 plus the log of z2. Okay, well, we're dealing with this multiple valued thing, and remember, it's all due to the behavior of the argument, the lowercase a argument. So let's run through the proof of that. Where we've got the log of the product equals the sum of the logs is the claim. Well, we've defined the lowercase l log function, log z, is a natural log of the modulus plus the lowercase a argument of z. We've seen in the past that the argument of the product is the sum of the arguments, which really foreshadowed their relationship to a log function. So if we take the multiple valued log function in the complex setting, log z1, z2, it is by definition natural log of the modulus of the product plus the argument of the product. Okay, here we're in the realm of the real natural log function, where the natural log of the product of two things is the sum of the logs, borrowing that from calculus or algebra. And we just stated that the argument of a product is the sum of the arguments, lowercase a argument. And we just group things together, and that produces the sum of the log z1 plus log z2. So, crudely put, the log of the product is the sum of the logarithms. Back to the notes. This previous result, it's not going to hold if we looked at the principal branch of the logarithm. We'd have problems with sums of principal arguments. Now, if we were to not have that problem with principal arguments, we could get a result along these lines. In fact, if we took complex numbers z1 and z2, where the real part of z1 is greater than 0, and the real part of z2 is greater than 0, so then the principal argument of both of these is between negative pi halves and pi halves. So when we take the sum of the arguments, we'll get the sum of the arguments between negative pi and pi. And those are still valid values for principal argument. So in that case, and this is actually an exercise in the book, in the event that z1 and z2 have positive real parts, then we can say the capital L log of z1, z2 equals the capital L log of z1 plus the capital L log of z2. That is the log function, the principal value of the log function based on the principal argument of the complex numbers. Similarly, we can show for non-zero complex numbers, z1 and z2, the lowercase l log function satisfies log of z1 divided by z2 is the log of z1 minus the log of z2. Log of the quotient is the difference of the logs, a familiar property. That's an exercise in the book as well. Lemma 3.32.c says if z is any complex number and n is an integer, then we have z to the n is e to the e to the n log z, familiar relationship. Notice that it's lowercase l, so we'll be dealing with a set valued stuff. Combined with the exponential function, though, some good things will happen. Let's take a look at the proof of that. Where we'll take z represented in terms of the lowercase a argument, multiple valued function. So we'll take z and write it as r e to the I theta, or if you like, as mod z e to the I lowercase a argument of z. We get the multiple values going into the exponential function. They're values that differ by multiples of 2 pi, and the e to the I will eat those up and produce 1. So the periodic behavior of the argument, lowercase a, argument is kind of devoured by the exponential e to the I, just like changing arguments by multiples of 2 pi in trig functions. Don't change the values of the trig functions. And Euler would tell you these are basically sines and cosines we're dealing with the e to the I theta type relationship. So we'll take z to be of this form. Now if we look at e to the log z, by definition, log z, lowercase l, that would be e to the natural log of the modulus of z plus I times the argument of z, lowercase l, lowercase a. We know properties of the exponential from the past. In particular, we can break this up as e to the natural log mod z, e to the I arg z. Hey, this is just real stuff here, e to the natural log mod z. So the natural log function, that's the natural log function from calculus in the real setting, composes with the exponential function, just to leave us with the mod z up front, e to the I arg z. Well, e to the I arg z times mod z is exactly what z is, as written up here, establishing that e to the log z is z itself, showing in some sense that the inverse of the exponential function is this log function. It's that multiple valued stuff that's somewhat in the way, but we have established that equality with the appropriate interpretation for the argument, lowercase a argument. So let's take n to be a natural number, and let's look at z to the n. Well, we just saw z equals e log z, so that's equivalent to replace z with e log z, that quantity to the n, when n is a natural number. These exponents mean repeated multiplication, so that gives us e log z, n times. We know how exponentials behave in terms of additions of the exponents in an exponential function. So we'll have e to the log z plus log z plus log z n times, producing this. It's lemma 3.29.a that tells us when multiplying exponentials, add exponents. So we've established the claim z to the n equals e to the n log z when n is a non-negative integer. The claim is for n any integer. So we need to take care of n negative. So let n be a negative integer. Z to the n, we know z is e log z. We now have that to the n power upon substituting. Okay, properties of logarithms allow us to do multiplication under these conditions. So we're going to put a negative sign here and a negative sign here. Those will cancel out when multiplying. And now n is negative, so negative n itself is positive, a positive integer. So we'll write out what it means to have something raised to a positive integer power. It's that something times itself this many times. The number of times is negative n here. Again, properties of exponentials say we'll add those exponents together. We'll have then e to the negative log z, negative n times. And now in this exponent, we've just got regular old multiplication, and the negatives cancel, producing z to the n is e to the n log z, establishing this now for the original claim, now for n a negative integer and a positive integer earlier, so the result holds for all integers n. Another claim about nth roots. We still haven't defined an nth root function, but we're closer than ever. Lemma 3.32.d states, take non-zero complex number C, and let n be a positive integer, a natural number. The claim is that e to the, or exponentiate, 1 over n log z, lowercase l, so it's a whole collection of numbers that are going into an exponential function. And the claim is what we're getting out is a whole collection of numbers, a set of numbers consisting of n distinct elements, each of which is an nth root of z. I'm back. So we're using exponential functions, it appears, to define roots of z. So let's look at a proof. Okay. Well, let's represent z as r e to the I theta, where theta is the principal value of the argument of z. That is, it's between negative pi and pi as given. Then, if we'll take 1 over n log z and exponentiate it, okay, log z, lowercase l, is defined to be the natural log of the modulus of z plus I times lowercase a argument. So we're generating that set of arguments by taking the principal value and adding multiples of 2, integer multiples of 2 pi I to that principal value. So we've got equality there by the definition of the lowercase l log function. Okay, here we're just distributing the 1 over n over both pieces. Properties of exponentials allow us to exponentiate the first part times exponentiating the second part. So we've broken this into exponential of 1 over n natural log mod z. Everything's real, so this won't be a problem. And then the exponential of this whole collection of angles, whole collection of arguments. So we'll take that, and to establish the claim, we need to take that quantity, equivalently this quantity, raise it to the nth power, and show that we get z out. And also observe that there are n different values here. Okay, the exponential with the imaginary numbers in it was of this form. We could rewrite that using Euler's formula in terms of sines and cosines. And as n varies, the periodicity here is going to produce n distinct values. We'll let k range from 0 to n minus 1. That'll give us different input angles. That'll give us different outputs from the exponential function. Of course, when k equals n, we're just adding a multiple of 2 pi inside both of those trig functions, and we're back where we started. It's wrapped around through the period of those trig functions. But for k equals 0 to n minus 1, we do get different values, and there's the collection of n distinct values. We need to show those values, when raised to the nth power, produce z, and that'll establish the claim. Okay, we left off on the previous page. It's labeled equation 7 to be consistent with the book. Take that e to the 1 over n log z. We had it expressed in this form, this product of exponentials. We need to raise that to the n, raise that to the n. Okay, so that's a repeated multiplication. That's one way to establish it. Here, the first part, we've just got regular old exponentials and real logs. So the exponential and the log combine as inverse functions of each other. We've got the 1 over n and the exponent of n. That'll combine down just to give us a mod z ultimately. Here, we're exponentiating. We've got the n. We could treat this as repeated multiplication and do the addition inside the exponential function. Effectively, the n exponent cancels with the 1 over n in the exponential, producing e to the I quantity principal argument of z plus 2k pi. Rewriting it in terms of the exponentials, the 2k pi, there's an I out front, will just produce multiples of 1. So we get e to the I capital theta, e to the I principal argument of z. And hey, mod z, e to the I principal value of z is z itself. And in fact, each of these numbers raised to the nth power does produce z. So we're going to denote that. This is the first time we've dealt with this as it relates to exponential functions. It won't be the last. We're going to denote z to the 1 over n, the nth roots of z as e to the 1 over n log z. This allows us to make that kind of notational claim. Back to the notes. We had established this actually just for n, a positive integer, also for n, a negative integer. That's one of the exercises. In the next section, we're going to look at more properties of logarithms, and these little 4 lemmas presented here will play a role there as well. So on to the next section.